Assalamu alaikum, Dr. Zeral and Dr. Hamzari. We are Group 8 of Avionics Systems, Semester 1, and today we will be presenting about flight control and management. My name is Mutaman Mohamed, and I will be starting, my matrix number is 204848, and I will be starting with the introduction of flight control and management. Airplane controls work precisely and physically. Just in little airplanes with the streamlined powers are not in a huge sum, so it is very rare nowadays to find airplanes which are worked mechanically. Push rods, pulleys, stabilizers, string links, and chains are an assortment of mechanical pieces of the manual flight control framework. The most basic flight control framework plans were mechanical, and they go back to the earliest airplanes. They work with an assortment of mechanical parts, for example, as mentioned, push rods, pulleys, stabilizers, string links, and chains here and there, just so they can send powers to the flight deck controls and to the control surfaces. Mechanical flight control frameworks are as yet utilized today in little broad and gain classification airplanes, where the streamlined powers are not outrageous. A bigger region of control surface was required. As time passed, a bigger region was needed because this manual control was not enough. A standard fixed plane flight control structures involve flight control. A standard fixed wing plane flight control structures involves flight control surfaces, the individual cockpit controls, interfacing linkages, and the urgent working frameworks to control a plane's course during flight. So this results in expansion in the powers required for them to move. Airplane flight controls are the methods or ways by which a pilot controls the course and mentality of an airplane in flight. Flight control frameworks are partitioned into two sections that are alluded to as essential and auxiliary flight, controls. That is all from me.
Greetings, Dr. Zario and Dr. Azari. My name is Joana, Trusa, and my matrix number is 207621. And I will be presenting about the history of flight control and management. So just like any other machineries, aircraft control systems also have evolved within the past 100 years. The aircraft from the first generations are the pioneers to the aircraft that we have today. And with the new demand for speed, aircraft designers have been pressured to produce a better and more responsive control methods for an aircraft. So in the very early days of the first generation, aircraft controls operate mechanically and manually. These systems are still being used today, but only in small aircraft where the aerodynamic forces are not in a very large amount. The Wright Flyer 1, Lariat, and Fokker-Eindecker, for example, are the earliest aircraft to operate manually, and they operate using this wing warping system. It is a system where no hinge control surfaces are used conventionally on the wing, and sometimes not even used during the pitch control, like on the Wright Flyer 1 and the original Ettridge Top 1909, which only had a rudder, and this rudder was either hinged or pivoting. Push rods, pulleys, counterweights, tension cables, and chains are a collection of mechanical parts that are responsible to transmit forces of flight on the controls of the cockpit directly to the control surfaces. They also have gust locks to protect the control surfaces and linkage from any damage caused by the wind. However, due to higher loads in large aircraft, higher airspeed in small aircraft has led to the requirement of larger area of control surface. This is due to the increase in the force required to move these machines. So pilots' strength has become a problem. So to help solve this problem, the hydromechanical system was introduced during the second and third generation to help break these limits. And this hydromechanical system consists of mechanical and hydraulic circuit. The mechanical circuit links the controls of the cockpit with the hydraulic circuit. Well, this hydraulic circuit consists of the mechanical parts, including the hydraulic pumps. These hydraulic pumps powers the actuators to convert hydraulic pressure into control surface movements. So the only problem now is economy. The pilot's strength was no longer a problem. Well, as usual, as technology progressed, it is always about saving time, saving energy. So the fly-by-wire system was introduced. The fly-by-wire system replaces almost all the mechanical parts with only wires. It saves fuel consumption because hydroliquids were no longer needed, so the aircrafts become lighter due to lesser mechanical parts. Maintenance is also simplified because there are fewer moving parts. How this fly-by-wire system work will be explained within the working principle.
Salam and greeting to Dr. Zaril and Dr. Amzari. So my name is Nurin Syazana Binti Mohamed. My metric number is 207071. And today I'll be presenting about the working principle of flight control and management. Okay, the first thing I'll be talking about the intro first, and then I'll go through to the primary and secondary flight controls. Okay, the flight control consists of various services around the aircraft, which allows the pilot to control the aircraft that manipulate aerodynamic forces on the plane. Okay, the primary flight controls are simply those flight controls that the pilot predominantly use, which the pilot always use, primary use, okay, to control the airplane. So the secondary flight controls is used to change the airplane's performance, and also at the same time, it lightens the pilot's workload. Okay, the primary flight controls are the ailerons, elevators, and rudders. And the secondary flight controls are the flaps and trim. We can see at the next slide, okay? Okay, as you can see on the screen, there is a purple color and blue color one. The purple color is the primary flight controls, which they show the rudder and elevators, and also the ailerons, while the blue one is the secondary flight controls, which they show the spoilers and then the flaps and trim. Okay, that is the image. Okay, so for the first primary flight control is ailerons. So aileron is located on the back end of the wings up towards the tip, as you can see on the image shown. And the function of ailerons is to control the aircraft's roll or bank. Okay, as you can see on the image, it has the right force. On the right aileron, it has the right force, and on the left aileron, it has the left force. Okay, so now we focus on the aircraft rolling to the left. Okay, when the pilot starts to move the controls to the left aileron, as you can see on the image, will be deflected up and create a downward force. And at the same time, the right aileron is deflected down, which creating an upward force. Okay, and then this results in the aircraft to roll to the left. Okay, next, in opposite, the same thing will be happen. When the pilot move the controls to the right aileron will deflect it down and creating an upward force. Okay, and then the left aileron is deflected up and create the downward force at the same time. So that is how the ailerons work. Okay, next, primary flight control is elevator. So the elevator is attached to the back of the horizontal stabilizer, as you can see on the screen. The function of the elevator is to control the airplane pitch, okay, which allows the airplane to climb or descend. Okay, when the pilot moves the controls forward or aft, the elevator will start to rotate and deflecting the air. Hence, it creates the force that affects in the airplane's pitch changing. Okay, that is how the elevator works. Okay, if you want to see how the elevator works, okay, you have to see this image. You have to scan this image. Okay, when the pilot pulls back the controls, the elevator will move up and then create a force that pushes the tail of the airplane down, and then making the nose pitch up and causing the airplanes to start climbing. So as you can see on your screen, the up elevator will make the airplane nose rises, while the down elevator, when the elevator is down, the airplane nose will drop. Okay, next, I'll be talking about the rudder, the third primary flight control. Okay, the rudder, as you can see on the screen also, it is attached to the back end of the vertical stabilizer. Okay, there's a cable connected to the rudder, which allows the rudder to move. Okay, when the air moves around the deflected rudder, a force is applied, and then they are making the airplane yaw. Okay, the yaw is movement of the nose of the aircraft is perpendicular to the wings. Okay. If the pilot pushes the left rudder pedal, the nose of the airplane will slide to the left. Basically, the rudder, they use the rudder in coordination with ailerons to control, to turn the airplane. Okay, they use the rudder. That is the rudder's function. Okay. Okay. Next, moving on to the secondary flight control. Okay, so that is the flaps. The flap, which you can see on the screen, okay, it is located on the backside of the wing which is close to the fuselage. Okay, the flap is primarily used to help increase lift during takeoff and also landing. Okay, so the pilot is controlling the flaps by moving a lever on the airplane, which is either electrically or manually. So when electrically moves the flaps, it is by a motor. When it is manually moved the flap, it uses a lever like on the Piper Arrow aircraft. Okay, so next we're going to show how the flaps working. Okay, as the pilot extend the flaps, the shape of the wing will change, which increases the lift, and it allows the airplane to fly at a slower speed and make the landing in steeper approach. Okay, so as you can see here, at the full flaps, it has a steeper descent angle, right? So it is actually beneficial during takeoff from a short runway, because it allows the airplane to use less runway as it takes off at a slower speed. Okay, the pilot uses the flaps to allow the airplane to land at a slower speed, using less distance to decelerate and stop, as you can see here in the image. Okay, there are full flaps, which consequence the airplane to land in a steeper approach, and half flaps, and then no flaps at all. Okay. Okay, next we move on to the secondary flight control, which is trim. The trim is located on the rearward or back end of the elevator, which you can see on the screen. Okay, the trim is typically controlled through a wheel inside the cockpit that is labeled nose down or nose up. Okay, when the pilot moves this wheel, the cables will calibrate the elevator trim tab. Okay, next. Okay, so normally during takeoff, the trim tab is in its neutral position, which means it's just flushing with the elevator. So as the pilot starts to climb, however, he or she may trim the airplane, okay, which is they do that to help relieve the control pressure and avoid pilot fatigue. So in order for the pilot to reach at a specific airspeed that they want, they can just simply adjust the trim to maintain the airspeed. Okay, we can see on the next slide.
Assalamualaikum and greetings to my lecturers and my classmates. My name is Miza Shazwina Binti Zaharum. My matrix number is 208222. And now I am going to continue the presentation by talking about the applications. First is the flight control application. It is distributed into two parts, which are auto stabilization system and fly-by-wire system, or we can call it as FBW. So what is the difference between auto stabilization system and fly-by-wire, FBW? So the auto stabilization system, they can carry out further calculations to revise the aircraft response. It is also necessary because they can control corrections. And the fly-by-wire system is introduced due to the speedy development and full growth of digital electronics. Most of the modern aircraft own it. It is because the weight savings, and they can also improve the handling characteristics. As an example is the Airbus A320 and A330 or A340, which are the stable transports, or the first Boeing, which is the Boeing 777. They uses fly-by-wire system. So next, going to move to the features of the FBW. First is the total elimination of all complex mechanical control runs and linkages, meaning all commands and signals are transmitted electrically along wires. This is why hence the name fly-by-wire system. The pilot inputs do not move the control surfaces, and the inputs are read by a computer to determine how to move the control surface, so they can achieve what the pilot wants. Next is between the pilot's commands and the control surface actuators of the interposition of a computer. So the control surfaces consist of two-stage servo system with the fly-by-wire servo actuators. So what is actuators? Actuators is actually a mover that can control or move the system. And it also senses feedback of the components of aircraft angular and linear motion. Next, FBW the air data sensors supply the height and airspeed information to the computer. It can acquire any process data from pitot and static pressure, data buses, and analog inputs to obtain key air data parameters such as altitude, airspeed for a safe flight. Lastly, it has the redundancy to enable failures in the system to be absorbed. That means the percentage of any failure to happen is very low. Next, we're going to move to the gains of fly-by-wire system. First, by using fly-by-wire system, fly-by-wire system has the ability to exploit aircraft configuration. What does this mean? It means that it has an aerodynamic efficiency, like lifting is increased, but the drag will be decreased for stability. This will also include the unstableness of the aircraft over the range of speed or height condition or flight envelope that is called negative stability. Next, the aircraft. So it will make amends for the loss of natural stability, so the aircraft will be lighter with a better performance. Now, before we move on to the flight management, let's discuss about the difference between the flight control and flight management. So flight control is actually under flight management. It is a part of the FMS, and the flight control is a computer system. So now let's talk about the uses of flight management. The first use is flight management guides the lateral and vertical control of the aircraft flight path, which is also known as the yaw and pitch movement. So this lateral and vertical, they are perpendicular to the others and they intersect at the aircraft center of the gravity. The yaw happens at the rudder and the pitch, which is the lateral, happens at the elevator of the aircraft. Next is the flight management monitors the aircraft flight envelope and computing the optimum speed for each phase of the flight. So flight envelope is actually the capability of a design in terms of airspeed and load factors. Next, flight management also controls automatically the engine thrust. So they will adjust the control levels for the engine. Lastly, flight management also plays a major role in flight planning tasks. Flight management, it means that they provide the computerized flight planning. This also means that they can revise on the flight plan just in case they have to come up with any changes. Next, flight management has two independent management systems, which is FMS1 on the captain side and FMS2 on the first officer side. So the cockpit interfaces to the flight crew provided by each FMS comprise of a keyboard and cursor control unit, KCCU. So KCCU, it will help navigations with the flight crew, and they also modify and enter data, MFD, which we will go into next. So what is MFD? MFD is a multi-function display. Multi-function display, they can provide into an aircraft position, flight plan, and performance. MFD is interactive, so that means it is possible to enter or modify data via KCCU. Next, we are going to talk about electronic flight instrument system, or also known as EFIS, and control panel EFIS-CP. So the EFIS, they control the graphical and textual flight management system data that appear on the ND and PFD. So that's why I didn't mention, I skipped PFD and ND. PFD is primary flight display and ND is a navigation display. So this is it, FMS1 on the right captain side, MFS2.
Hello, thanks for joining. Greetings, Doctor. We came to the end and we're going to discuss the conclusion for the flight control management. One of the most practiced and well-known behaviors of humans is flight control by human pilots. And in order to characterize and forecast human control efficiency and workload, there have been mathematical models which have been developed to extend a wide variety of important issues such as aircraft handling characteristics, display and control system, design and analysis, and design of the usage of simulators. As a development tools, these models do not replace the human-in-loop simulation, but instead it supplements it. It supplements the simulation, the flight testing, and the more traditional study of human factors. There are a range of daunting problems and areas of study that remain or are emerging despite its high degree of understanding of human control that has been achieved, and the achievement listed above. The evolution of aircraft control, the aircraft control and display systems and mission parameter, they pose a new control challenge. Therefore, we have a revolutionary aircraft configurations with different dynamic features, especially when highly enhanced, like the 6 degrees of control, 6-degree freedom of control, excuse me, the different flying routes, and so on. These modern systems are now well known to the least, with pilot-induced oscillations, excessive pilot workload, and insufficient pilot vehicle interfaces. And there have been persistent design difficulties. So for such tasks, there is a need for both data and expansion of the predictive capabilities of pilot models. And it poses a new challenge for the future too. But flight control has came a long way since the hydraulic pumps to the fly-by-wire system that is happening for now. And it certainly has proved itself. But with the excessive certification processes the regulatory bodies do, modern flight control has certainly proved itself in the eyes of the FAA and the EASA, the regulatory bodies in the US and Europe, but it still has a lot of challenges ahead. Thank you for joining.